Welcome to lecture number 17 of this course, Nonlinear Structural Analysis, Theory and Applications. Let's recall what we did in the last lecture. So, in the last lecture, we looked at some of the simple idealized mathematical models for simulating the stress strain response. Okay. So, starting from rigid plastic, which is not so widely used, we looked at elastic perfectly plastic, bilinear plastic, then we looked at Ramberg Osgood, Geoffrey Menegotto Pinto and so on. Okay. So, in this lecture we want to talk about hardening rules and how they dictate the cyclic stress strain response of different materials. So, these are the three different hardening rules that we will be talking about, and using a very simple example, I will demonstrate isotropic hardening, kinematic hardening and independent hardening rule. Okay. So, if you recall from the second last lecture where we talked about the work hardening or also called strain hardening. So, basically as I said earlier, the material has memory. The inelastic material or the hysteretic materials have memory. If you have taken the material above its initial yield strength, right, and you have unloaded it, the next time you take the material, then what happens up to that increased strength. So, if I draw, it is something like this. So, let us say I am drawing sigma versus epsilon, and let us say here up to here it is linear elastic, and then this is the behavior of the material, right. Now, I have taken this material like so up to this point, right. So, this is let us say my sigma y0, okay, and this is the corresponding yield strength, right, and I have taken this material up to this point, okay, and then I have unloaded it. So, what happens? It comes back elastically. This has the elastic modulus E. So, next time I reload this material from this point, it will follow this path. So, that means up to this point material behaves linear elastically and then it increases, right. So, that means the yield strength of the material has increased due to this hardening. It is just like if you have taken a very difficult course in the last semester, okay, and this course is let us say not so difficult, then what happens? You will be able to handle it very easily, right. So, that means you have already gone beyond your limit, if I can call, in the last semester, and this time this is going to be very easy. So, just like the material is responding linear elastically. Okay. So, how do we handle this hardening? So, typically what is done, we introduce a parameter called kappa, the hardening parameter, to characterize various stages of hardening. And you remember from the previous lecture we talked about the plastic modulus, which is the slope of the tangent to the sigma and epsilon p curve, right. So, it looks something like this. The slope of this is the plastic modulus E sub p. So, what is done? E sub p is assumed to be a function of the hardening parameter kappa. Okay. We will not get in so much of the mathematics, but we will try to understand physically what happens. So, the kappa, there are several choices for kappa. Some of the choices are the kappa can be the plastic work. Plastic work means it is integration stress into incremental plastic strain. It can be the plastic strain itself, or it can be the accumulative plastic strain, okay, which I can say that every incremental loading the plastic strain is d epsilon p, and I want to take the magnitude only. Okay. So, therefore, I am multiplying this two and then taking the square root. So, this is the magnitude of the incremental plastic strain, and you keep adding the incremental plastic strain to get the accumulative total plastic strain. So, kappa can be E sub p. So, just to give you an example, the functional form of EP, this can be determined from laboratory test, and a similar work was done in 1994 by Rickles and Popov, where they have found that the plastic modulus for an application which was eccentrically braced frame. Okay. So, plastic modulus is equal to EF into 1 plus beta into e raised to the power minus alpha into epsilon p. So, if I make a plot of this equation, it looks something like this. So, I am plotting I am plotting the plastic modulus EP with the plastic strain epsilon p. Okay. So, initially it has a value 0 EP0, which is what? Which is EF into 1 plus beta, right? And then what is the variation? It varies like this. Okay. So, the final value asymptotically approaching to a final value, what is that? That is EF. Okay. So, as you can see that the plastic modulus is varying like this, and what is alpha and beta? Well, alpha beta are material constant that are determined from laboratory experiment. This is just an example. Okay. So, now for material under reverse cyclic loading condition, the subsequent yield stress is usually determined by one of the following three hardening rules: isotropic, kinematic or independent hardening rule. Using simple example, I will demonstrate each one of this rule. So, what is isotropic hardening rule? Let us take the example of a bilinear stress strain response. So, this is let us say in tension, okay, and this is in compression, and I have the same stress strain response in tension and compression, which is typically true for ductile material. Okay. So, initially sigma A is equal to sigma A prime. That means I am saying this is equal to that in magnitude. Okay. So, now I have loaded the material, I have gone past this initial yield strength and gone like that. So, I have gone to point B, right. Now, I unload. So, here my unloading is complete at point C, and then I load it in compression, right, and then the material yields at point B prime. So, according to isotropic hardening, what is assumed that the reverse compressive yield stress is assumed equal to tensile yield stress before the load reversal. So, that means this stress is assumed to be same as that. Okay. So, sigma B prime magnitude is equal to sigma B. In other words, I can say the length of this line B B prime is larger than that of A A prime. Okay. So, as you can see, this isotropic hardening neglects the Bossinger effect completely, because Bossinger effect means if you have taken it beyond the initial yield, it should have yielded earlier in compression and vice versa. So, mathematically this can be expressed as the magnitude of the yield stress is a function of this parameter kappa. We will not get into the mathematics too much. Okay. You can say BC is equal to B prime C. This length of this line and this line are equal. Okay. On the other hand, in kinematic hardening, what is done? The elastic range is assumed to be unchanged during hardening. What is meant by that? Well, we have taken this material up to point B and unloading and then loading in compression, the material yields at point B prime. So, according to this rule, it is assumed that the length of this line B B prime is equal to A A prime. Okay. So, you have taken this sigma B is greater than sigma A. So, naturally sigma B prime in magnitude is going to be smaller than sigma A prime. Okay. So, from here to here is equal to from here to here. So, this is the center of the elastic region which is moving along this line. What is the slope of this line? Well, the slope of this is, if I say alpha E, where alpha is the strain hardening ratio, then this slope is also alpha E. So, the center of this elastic region, which is here, if I let us say draw another one from here, let us say if I go like that and unload, then this center of the elastic region is going to be here and this will yield here in compression. Okay. So, that is the kinematic hardening. Mathematically, one can write this sigma minus C, which is a function of the hardening parameter kappa, and the magnitude of that is equal to the sigma 0, which is the yield strength. Okay. Now, let me talk about the independent hardening. So, independent hardening means material is assumed to be hardening independently in tension and compression. Okay. So, that means if I have taken this material to point B, so I have gone past the initial yield strength in tension. When I unload and load it in compression, the material in compression behaves like a virgin material. It does not remember what has happened in tension. Okay, that is the whole idea. That means sigma B prime is equal to sigma A prime. Okay. So, in this figure we can say that BC is greater than OA because I have gone past the initial yield strength sigma A, okay, but CB prime, this one is equal to OA prime because the material does not remember that it has been taken beyond sigma Y0 in tension. Okay. So, mathematically what we can do, we can introduce two different kappa parameter, one for tension and one for compression to handle this hardening. Okay. Now, to explain this, I will take a very simple example. Okay. The example goes like this. It is taken from the book by Chen and Han, Plasticity for Structural Engineers, from chapter 1. Okay. The sigma epsilon response in simple tension for an elastic linear work hardening plastic, which we also call bilinear plastic material, is approximated by sigma is equal to the yield strength plus a constant m into the plastic strength epsilon p when sigma is greater than sigma Y0. Otherwise, it is simply elastic E into elastic strain. Okay. So, the experiment was, let us say, conducted and sigma Y0 is 207 MPa, the modulus of elasticity is 207 GPa, and this M is determined to be 25.9 GPa, right. A material sample is subjected to a strain cycle like this. Initially, the material is at 0 strain, then I apply positive means tension. So, I apply 0.007 strain in tension, then unload it and it may get reloaded, it may get loaded in compression, but I take it to 0.007 to 0 strain, right, and then again take it to 0.007 strain. So, sketch the sigma epsilon curve considering isotropic hardening, kinematic hardening and independent hardening. Okay. So, let us remember or make note of these numbers and let us try to solve this example. So, what is the plastic modulus? Well, if I differentiate this equation with epsilon p, then I get the plastic modulus. So, if I differentiate this, what do I get? I get m, right. So, d sigma d epsilon p is equal to m, which is a constant. So, the plastic modulus in this example happens to be a constant, which is given 25,900 MPa. Okay. So, what is the tangent modulus? Tangent modulus is, as we have calculated, Et is EEP divided by E plus EP, which is also constant for this particular example. It is a very simple example. So, now let us start to construct the sigma epsilon response. So, where do we get the first yield? Well, the yield strain is sigma Y0 by E. Sigma Y0 is 207 MPa and modulus of elasticity is 207 GPa. So, that gives me 0.001. That is the strain at which first yielding occur. Okay. So, now I want to calculate what is the stress at 0.007. Remember, we are taking it from 0 to 0.007 and then back to 0 and then again to 0.007, right. So, now from 0 to 0.001 material has yielded. So, what is the state of stress at 0.007 that we want to calculate? We have the tangent modulus. Okay. So, what I will do, sigma Y0 plus the incremental stress. What is the incremental stress? Sigma Y0 plus tangent modulus into incremental strain. What is the incremental strain? Well, 0.007 is what I wanted to apply and I already have applied 0.001. So, this is the incremental strain multiplied by the tangent modulus, which is coming from here. This is the yield strength. So, that gives me 345 MPa. Okay. And this is independent of any hardening rule. Okay. That means, if I show you, so this is the 0, we have gone up to this point, which is 207 MPa, okay, for all of them, 207, this is 207. So, this first one is for isotropic hardening, this is kinematic hardening, this is independent hardening, and I will be explaining each one of them. Okay. So, then at 0.007 strain, here we come to this point A, which is same in all three cases because it is independent of hardening. And what is the stress we calculated? We calculated this is 345 MPa. Okay. Now, let us look at each one of them. So, if I first look at the solution for isotropic hardening, right? Solution for isotropic hardening. So, I have taken to point A. Now, this is 0.007. I have to now go to 0 strain. So, I will unload elastically, right, and the material behavior remains elastic until it yields again in compression. Now, where does it yield? So, it yields at point B. Now, what is the stress at point B according to isotropic hardening? So, according to isotropic hardening, material yields at point B where sigma B is equal to sigma A in terms of magnitude, right. So, sigma B is negative of sigma A because I am using compression negative. Okay. So, that is minus 345 MPa. This is minus 345 MPa. Okay. And this is 345 MPa. Okay. Now, what is the strain at this level? This is epsilon B. What is the strain at this level? Well, which is easy to calculate. I know the strain here. I know from here to here what is the total stress, okay, that is 2 times sigma A. So, epsilon A minus 2 times sigma A divided by E, that gives me 0.00367. So, that is the strain at point B. Okay. Now, I have to go to 0 strain. I have gone up to 0.00367. So, what will happen? The material will continue to strain harden in compression up to this point where there is a strain reversal, right. So, what is the stress at point C? How do I calculate? Okay. So, material continues yielding in compression until you reach point C. At point C, what is the strain? That is given 0. Then how do I calculate this sigma C? Sigma C is sigma B plus the tangent modulus times the incremental strain. So, minus 345 plus this is my tangent modulus, incremental strain, the final strain is 0 and this strain is, this is plus 0.00367 with a minus sign here because final strain minus initial strain. So, that gives you 429. So, that means this point is minus 429. Okay. Now, I am going from 0 to 0.007. So, what will happen? The material will unload elastically, reload in tension elastically until it yields at point D. What is the stress at point D? Well, this subsequent yield stress at point D is equal to, according to the isotropic hardening rule, it is equal to sigma C in magnitude. So, sigma D is minus sigma C, which is 429. So, this is 429, I am just writing here. So, this is 429. Okay. What is the strain here at point here? This is epsilon D. So, epsilon D also I can easily calculate epsilon C, which is the strain here, that is 0 plus this total from here to here divided by the modulus of elasticity, that gives me 0.004145. Okay. Now, I have to go to 0.007. So, then the material will continue to yield and strain harden in tension, okay, up to 0.007 or up to the point E, which is my target strain. Okay. So, how do I calculate? At point E, the target strain is 0.007. So, the stress here sigma E is the sigma D plus this incremental stress, which is tangent modulus times the incremental strain, that gives me 495. Okay. So, we end up here at 495 according to the isotropic hardening rule. Now, let me look at kinematic hardening rule. So, we have what we have done from independent of hardening, we have gone up to this point A, right. Now, according to the kinematic hardening, what happens when I take the material from point A to 0 strain? Okay. So, material will unload elastically, unloading completed here, okay. Then elastically load in compression up to the point B where it yields. Okay. According to the kinematic hardening rule, if you recall, this length is equal to that length, right. If I draw the virgin material stress strain response, which is up to this. Okay. So, that means this length is equal to that length. So, from there I can calculate sigma b. So, sigma b is my sigma A, the stress here, minus 2 times the yield strength. Okay. So, that gives me minus 69 MPa. So, the stress here is minus 69 MPa. Once I have established the stress, I can calculate the strain, which is epsilon A minus this. How much is this? Well, 2 sigma y0 divided by E. So, that gives me 0.005. I have to go to 0 strain. So, we are here at 0.005. So, material will continue to yield in compression with strain hardening. Okay. So, at point C the strain is 0 and I know the tangent modulus, which does not change, happens to be constant in this case. So, minus 69 plus tangent modulus times the incremental strain, that gives me minus 184 MPa. And then from point C we go to again 0.007. So, upon strain reversal the material will unload in compression, reload in tension elastically until it yields at point D. What is point D? Well, the point D must be lying on this line, isn't it, according to the kinematic hardening rule. So, sigma D is equal to sigma C plus 2 times sigma y0, that is 230 MPa, and epsilon D again epsilon C plus 2 sigma y0 by E, which is 0.002, right, and we have to go to the target point E, which with a strain of 0.007. So, upon continued loading, what we get, if sigma E is equal to sigma D, the stress at this point, plus tangent modulus times the incremental strain. So, here the strain is 0.002 and here the strain is 0.007, you get 345. So, according to the kinematic hardening rule, A and E basically coincide. Okay. Now, let us look at independent hardening. So, the material does not remember what has happened in tension when you take it to compression and vice versa. Okay. So, we have gone up to this point, right. Now, when I unload it, it gets unloaded and then it gets loaded in compression linear elastically until it yields at point B. What is sigma B? So, sigma B must be equal to the initial yield strength, because material does not remember what has happened in tension. Okay. So, sigma B is equal to minus sigma y0, that is minus 207 MPa. So, then I can similarly calculate what is epsilon B. Epsilon B is the strain here minus sigma A plus sigma y0. Okay. Note the change here, divided by E. So, that gives me 0.00433 strain, that is at this point. Okay. Basically, what I am doing from here to here, this is your sigma A plus sigma y0. Okay. And then the material will continue to yield in compression with, of course, strain hardening, and at point C the strain is 0. I can calculate the sigma C is equal to sigma B plus tangent modulus into incremental strain, which gives me minus 307 MPa. Now, when I unload in compression, I come to this point and elastically reload in tension, and until the material yields at point D. What is the stress at point D? So, according to the independent rule, again the material does not remember what has happened in compression, right. So, in tension the material was earlier taken to point A. So, then the stress here should be same as that of point A. So, that means sigma D must be equal to sigma A. Okay. So, sigma D is 345 MPa. Once the stress is established, then I can calculate epsilon D, which is same as before, epsilon C plus this length divided by modulus of elasticity. Okay. So, that is giving me 0.00315. Okay. Now, upon continued loading, epsilon reaches a target value. Our target value is 0.007 and this will continue with the same slope, right. The tangent modulus is constant. So, sigma E is equal to sigma D plus tangent modulus into incremental strain, which gives you 434 MPa. Okay. So, if I compare all three, what do you see? Very different stress strain response for this simple bilinear plastic model, depending on what we have assumed, isotropic hardening, kinematic hardening or independent hardening. Note that here the plastic modulus was constant, it was not a function of the parameter kappa. There are examples in this book by Chen and Han, you may take a look where the plastic modulus is a function of the plastic strain, accumulative plastic strain and the plastic work. Okay? But we will not get into those, we will be mainly focusing on the phenomenological model to do the stress strain response. Okay? So, in summary, we have explained three hardening rules: isotropic, kinematic and independent hardening rule. Now, which hardening rule is to be used? So, the answer is that depends on your application. Okay? So, that depends on the problem at hand. Okay? So, with that we will stop here today, and these are the references, okay, that you may want to use. So, in the next lecture what we will do? We will now look at the stress strain response, hysteretic or cyclic stress strain response for various materials. Primarily we will be looking at stress strain response or stress strain models for steel. That means the Geoffroy-Menegotto-Pinto model when it is extended or when it is applied for cyclic loading, as well as the Ramberg-Osgood, and then we will subsequently look at stress strain models for concrete and a very popular model called Bocoen model, which can be applied to many different which can be applied to simulate hysteretic response of many different materials and structural components. So, we will be looking at those models. Thank you.